If two miscible liquids of densities ρ1 and ρ2 are mixed, if their masses are equal, so we can say effective density ρ2 ρ1 ρ2 by ρ1 plus ρ2, and if their volumes are equal, then we can say ρ1 plus ρ2 by 2 is the effective density. Hi friends, welcome to the 9th video lecture of our crash or revision program for NEET and JEE. The chapter is fluids, mechanical properties of fluids. Okay. Mixing of liquids. Mixing of liquids. When two immiscible liquids are mixed, liquid with higher density will come to the top and liquid with lower density will go to the bottom when two immiscible liquids are mixed. And when two miscible liquids are mixed, then what will be the effective density that we are going to calculate here. When two miscible liquids are mixed, liquid 1 whose mass is m1, volume v1, density ρ1, and liquid 2 whose mass m2, volume v2, and density ρ2, then what will be the effective density? Rho effective we can say density is mass by volume, so total mass by total volume, m1 plus m2 by v1 plus v2, m1 plus m2 by v1 plus v2. If volume is not given, only mass and densities are given, then we can change this equation into rho effective equal to, I am giving this as equation number 1. So if volume is not given, only mass and densities are given, then rho effective we can write m1 plus m2 divided by, for volume we can write mass into density, because density equal to mass by volume, then volume equal to, mass by density, volume equal to mass by density, so we can write m1 by ρ1 plus m2 by ρ2, m1 by ρ1 plus m2 by ρ2. If masses are same, then what will we get? M will be cancelled, 1 plus 1 we will get 2 by 1 by ρ1 plus 1 by ρ2. By calculating we will get rho effective equal to, we will get 2 ρ1 ρ2 by ρ1 plus ρ2. So we can say effective density when two miscible liquids of densities ρ1 and ρ2 of equal amounts are mixed. If their masses are equal, then we can say rho effective equal to 2 ρ1 ρ2 by ρ1 plus ρ2. And equation number 1 we can again rewrite how, if mass is not given, volume and densities of the liquids are given. If mass is not given, so we can change the numerator, mass equal to volume into density, because density equal to mass by volume. So rho effective equal to, if mass and if volume and densities are given, mass is not given, so instead of mass we can write volume into density. So ρ1 v1 plus ρ2 v2 divided by what? v1 plus v2. If mass is not given, question number we can change like that. Now if volume is given, if volumes of the liquids mixed are equal, then what will we get? Rho effective equal to, or effective density equal to v1 plus v2 by 2. Arithmetic mean, ρ1 plus ρ2 by 2. Arithmetic mean of densities. and this is the harmonic mean of density. So we can say if two miscible liquids of densities ρ1 and ρ2 are mixed, if their masses are equal, so we can say effective density ρ2 ρ1 ρ2 by ρ1 plus ρ2, and if their volumes are equal, then we can say ρ1 plus ρ2 by 2 is the effective density. Pressure due to liquid, that is calculated using P equal to PL. I am writing PL to understand pressure due to liquid. Okay, is given by the equation H rho g, where H is the depth of liquid column. Here H is not height, you have to take depth from the liquid surface. H is the depth from the liquid surface. Rho is the density of liquid, and g is the acceleration due to gravity. G is the acceleration due to gravity. So this is the pressure due to liquid, PL. And what is hydrostatic pressure? Hydrostatic pressure is the pressure due to all fluids. Hydrostatic pressure means pressure due to all fluids. Pressure due to all fluids. Here normally we have atmosphere here. Okay, so hydrostatic pressure means atmospheric pressure plus pressure due to liquid. Atmospheric pressure plus pressure due to liquid. Atmospheric pressure is denoted using P naught. Okay, that is equal to P equal to P naught plus H rho g. This is the hydrostatic pressure. Total pressure due to all fluids. That is hydrostatic pressure. And gauge pressure. Gauge pressure means difference between hydrostatic pressure and atmospheric pressure. Gauge pressure means difference between atmospheric pressure and hydrostatic pressure, P minus P0, that we will get here pressure due to liquids only, equal to pressure due to liquids. So gauge pressure is the pressure due to liquids only, and hydrostatic pressure is the pressure due to all fluids including atmosphere. And in mercury column, in mercury barometer, height of mercury column is 76 centimeter or 760 millimeter. So we can say that atmospheric pressure, we can give the values of H 76 centimeter or 76 into 10 power minus 2, and rho, density of mercury, 13.6 into 10 raised to 3 kilogram per meter cube, and G 9.8. We will get 1 atm, atmospheric pressure, equal to 1.013 into 10 power 5 Pascal. That is equal to 1 atm pressure. That is equal to 1 atmospheric pressure, and that is equal to 1.013 bar. 1.013 bar, because 1 bar equal to 10 power 5 Pascal. 1 bar equal to 10 power 5 Pascal, and that is equal to, we can say, 760 torr. That is equal to 760 torr. Torr is the practical unit of pressure. Okay, 1 torr equal to pressure due to 1 millimeter height of mercury. 1 torr equal to pressure due to 1 millimeter height of mercury. So we will get 1 torr equal to what? 133 Pascal. 1 torr equal to 133 Pascal, and in mercury barometer it is around 760 millimeter height of mercury. Okay, so 1 torr equal to 133 Pascal, and 760 torr is the 1 atm pressure, that is equal to 1.013 into 10 power 5 Pascal, and that is equal to approximate 1 bar. 1.013 bar, approximately 1 bar, it is around 10 power. 1 bar is 10 power 5 Pascal. Okay. If water is used instead of mercury in barometer, if water is used instead of mercury in barometer, then what will be the height of, what should be the height of water column? We know that pressure should be equal to H rho G. Then H equal to what? P by rho G. We are here calculating height of water column to balance atmospheric pressure. So atmospheric pressure is 1.013 into 10 power 5 Pascal divided by density of water is 10 raised to 3, and for G we can give approximate 10. 9.8, then we will get 10 cancelled, 10 power 1 will remain on numerator. So height of water column will be around 10 meter. Height of water column should be around 10 meter if water is used instead of mercury in barometer. And then height of mercury is very low, very small, around 76 centimeter only, because density of mercury is very large, 13.6 into 10 power 3 kilogram per meter cube. So if we are using low density liquids in mercury barometer, height of the liquid column should be very large to balance atmospheric pressure, and height of the liquid column should be very small if we are using very high density liquids. And in open tube manometer, it actually measures pressure of a system. You can see diagram, the P indicates pressure of the system, and that P should be measured using the pressure difference provided by the liquid level. Pressure difference provided by the liquid level. Initially, if P is not connected there, liquid level should be same in the column. Liquid level should be same in the in that U tube. Liquid column should be same. If P is connected, what happens? Due to the effect of P, liquid level increases in the right tube. Liquid level increases in the right tube. So we can say P is equal to pressure due to liquid due to that height difference. Okay, so we can say open tube manometer, which is opened at one end, open tube manometer measures pressure of systems, and the concept behind this, it is pressure due to liquid or gauge pressure is directly proportional to height of the manometer liquid. Height of the manometer liquid indicates the level change in levels of liquid. Okay, that is the concept behind open tube manometer. It is used to measure pressure of systems. Pascal's law. Pascal's law. The pressure given at any point of the liquid is equally transmitted to all points of the liquid. That is what discussed by Pascal. Okay, so we can say pressure at one end should be, one side should be equal to pressure at the other side. So P2 equal to what? P1. So pressure F2 by A2 equal to what? F1 by A1. So F2 equal to F1 into A2 by A1. F1 into A2 by A1. So we can say as A2 increases, F2 increases. As A2 increases, F2 increases. So by giving small force at the other end, at one end, we will get very large amount of force at the other end. It is the principle of hydraulic lift, hydraulic press, etc. So as A2 increases, F2 increases. So we can say the output force F2 is directly proportional to the output area A2 because the pressure is constant. Same at the two tanks. Archimedes principle. The principle says that when a body is immersed partly or fully in a liquid, then it will get a vertical upward force which opposes the weight. Okay, or we can say it will get a reaction due to the liquid or the fluid. Okay, then that vertical upward force which opposes the weight is called buoyant force. B-U-O-Y-A-N-T, buoyant force or upthrust. Buoyant force or upthrust, and it can be calculated using the equation FB equal to V inside into sigma G. V inside into sigma G. The sigma is actually density of the liquid. Okay, and V inside is the immersed volume of the body. Immersed volume of the body, and G is the acceleration due to gravity. This upward force is equal to weight of the displaced liquid. This upward force is equal to weight of the displaced liquid. So we can say body feels weight loss when it is placed in a liquid. So apparent weight of the body equal to actual weight minus upthrust. Actual weight minus upthrust. Apparent weight W dash, or we can say mg dash equal to actual weight mg minus, for upthrust we can say V inside into sigma G. For upthrust we can say V inside into sigma G. If volume is fully, if body is fully immersed, for fully immersed body, for fully immersed body, we can say V inside should be equal to V, volume of the body. Okay, and for volume we can write, for density we will write mass by volume. So for volume we can say mass by density, m by rho. M by rho. So we will get mg dash equal to mg minus m by rho into sigma G. M by rho into sigma G. M we can cancel out. So we will get G dash equal to G into 1 minus sigma by rho. This is the acceleration, effective acceleration due to gravity acting on a body fully immersed inside a liquid, and whose weight, apparent weight equal to mg dash. I can multiply this with m. Okay, then we will get apparent weight. So here sigma is density of the liquid and rho is the density of the body. Okay, and from here we can say upthrust is what? Upthrust is what? Apparent actual weight minus apparent weight. So we can say FB, upthrust equal to actual weight minus apparent weight. Weight minus weight dash. Actual weight minus weight loss in liquid is actually what? Weight loss in liquid is actually denoted using upthrust or buoyant force. Side heading, flotation. A body will float in a liquid if its density is less than or equal to density of the body. If density of the body is greater than the density of the body, the density of the liquid, the body will sink inside the liquid. So we can say its weight dominates above the buoyant force. That is why body is sinking inside the liquid and it goes to the bottom of the pot or vessel. Okay, if density is equal to density of the liquid, then what will happen? Then we can say body will float inside the liquid just below the liquid surface because their densities are same. And if density of body is less than density of the liquid, then body will float in the liquid with some part of the body inside the liquid. Okay, so for the flotation we can say density of the body should be less than or equal to density of the liquid, where rho is the density of body and sigma is the density of liquid. This is known as law of flotation. This is known as law of flotation. So while floating or during floating we can say weight of the body is balanced by upthrust. Weight of the body is balanced by upthrust, then only it can float. Otherwise it will sink. If weight is greater than, weight is not balanced by upthrust, body will sink. So while floating weight should be balanced by the upthrust. So for weight we can say mg, and for upthrust we can say V inside into sigma g. For mg we can write V rho g equal to V inside into sigma g. From here we can find what is the immersed part of the body. What is the volume of immersed part? That should be found using V inside equal to what? Gg will be cancelled. V into rho by sigma. Okay, this is the equation to find the portion, how much volume is included or immersed inside the liquid. Here you can see a question. A homogeneous solid cylinder of length L, capital L less than h by 2, cross-sectional area A by 5 is immersed such that it floats with its axis vertical at the liquid-liquid interface with the liquid L by 4 with the length L by 4 in the denser liquid as shown in the figure. The lower density liquid is open to atmosphere having pressure P0. The density D of the solid is given by. But there are two immiscible liquids, they are not mixed. So the body lies one part in the lower liquid and the other part in the higher liquid. Okay, lower density liquid on the top and higher density liquid at the bottom. Here body is at rest there, it is not sinking to the bottom of the vessel. So we can say weight of the should be is balanced by upthrust due to two liquids, because the two liquids are displaced with the displaced due to the body. So we have to take upthrust due to both the liquids. Weight, we have to find density of the body, right, in terms of density of liquid. So weight we can write mass into gmg. For mg we can write v rho g. So v rho g equal to, okay, v1 sigma 1 g plus v2 sigma 2 g. Here v1 v2 represents volume of solid part inside the liquids 1 and 2. For volume V we can write area into height. Area into height. For the body area is taken as A by 5, right? Area is taken as A by 5. A by 5 into what is height h, that we can write L, length of the solid cylinder, into rho, density of liquid, that we have to calculate. G will be cancelled, equal to volume V1 A by 5 into, in first liquid volume is, length is 3L by 4. 3L by 4 into sigma 1. Sigma 1 is D plus V2 area A by 5 into length L by 4 into density is 2D. Now we will get A by 5 area is cancelled. Length L also cancelled. Okay, here we will get rho equal to 3D by 4 plus 2D by 4. That is 5D by 4. 5D by 4 is the density of the body. Option A is the right answer. Viscosity. Viscosity actually means fluid friction. Fluid friction. That means the opposition between the liquid layers for the flow. Okay. You can see here a diagram. The liquid layer at the top moves with a larger speed and the liquid layer at the bottom moves with a small speed. So there is a cohesive force between the molecules of different layers. So when the liquid layer in the when the liquid molecule in the top layer moves with a larger speed, due to the cohesive force between the molecules of the top layer and the lower layers, the movement of molecules in the fastly moving liquid layer is opposed. That property is called fluid friction or viscosity. The viscous force can be calculated using the equation F equal to minus eta A dV by dx. Here F is the viscous force and eta is called coefficient of viscosity. And A is the area of liquid layers and dV by dx is called velocity gradient. Velocity gradient means change in velocity of liquid layers perpendicular displacement with respect to perpendicular displacement dV by dx. Okay. Negative sign indicates viscous force acts opposite to the direction of motion of liquid layers. Eta is called coefficient of viscosity, and this equation we can rewrite as F equal to minus eta simply V by L. V by L if velocity is not given as a function of displacement. So L is the perpendicular displacement of liquid layers. L is the perpendicular thickness of liquid layers. Okay, and V is the velocity of liquid layers. From here we can say eta equal to what? Eta equal to F by A into dV by dx. F by A into dV by dx. Eta is always taken as positive. We are not taking the negative sign here. Eta equal to F by A into dV by dx. So to get unit of eta for force Newton, area meter square, and dV velocity meter per second, and dx is displacement meter at the bottom. So meter will be cancelled. Second will go to the top. So unit of eta is Newton per meter square is Pascal, unit of pressure. So we can say Pascal second. Second will go to the numerator. Unit of eta is Pascal second, or it is called PL. PL is actually what? Torricelli. PL is actually Torricelli. Pascal second is Torricelli. Okay. 1 Torricelli equal to 1 Pascal second. Sorry, second small letter. 1 Torricelli equal to 1 Pascal second, or 1 Newton per meter square into second, because Pascal is unit of pressure. Poise is Poise is the CGS unit of eta. Instead of Newton, we have to take dyne. Instead of meter, centimeter. So we can say 1 poise equal to 1 dyne second by centimeter square. 1 dyne second by centimeter square. So we can say 1 poise LE equal to 1 poise LE equal to 10 poise. 1 poise LE equal to 10 poise, because poise is the CGS unit and poise LE is the SI unit. Then 1 poise equal to 0.1 poise LE. 1 poise equal to 0.1 poise LE. For example, viscosity of water is 0.01 poise. Then in poise LE it is 0.001 poise LE. Eta water, viscosity of water is 1 millipoise LE or 1 centipoise. What I have to write here I can write viscosity of water is 1 millipoise LE, 10 raised to minus 3. That is equal to 1 centipoise. Centi means 10 power minus 2. Here 1 poise equal to 0.1 poise LE. Okay. So in questions for entrance, viscosity is generally given in CGS unit poise. So while doing problems, we have to convert that unit into poise LE. Okay. Next, Stokes law. Stokes law. When a sphere of radius small r is moving through a fluid of viscosity eta with velocity v, then it will get a fluid friction or opposing force. Viscous force F equal to 6 pi eta RV, or for radius you can use small a, then 6 pi eta AV. Here you can use F equal to minus also, because velocity force acts opposite to the direction of velocity. That equation is found by George Stokes. No need of the proof, just by head the equation F equal to 6 pi eta RV. Then when a sphere of radius r is falling or moving through a liquid, it will get, in addition to its weight downwards, a buoyant force and viscous force upwards. A buoyant force and a viscous force upwards. When the body just falling to the liquid, it experiences both forces upwards. At a moment, the body reaches the equilibrium condition. That means the net force is 0. That means whose acceleration becomes 0. At equilibrium, whose net force will be 0, then its acceleration should be 0. That means its downward force weight is balanced by both viscous force and buoyant force. So we will get weight equal to Fb plus Fe for weight mg, that we can write V rho g, V sigma g buoyant force, and 6 pi eta Rv is the viscous force according to Stokes. Giving the values, you will get, you can cancel pi. Now here r cube, here r cube, here r, so you can make this r as square. Okay, 4, 4, 6, so making for 2, 2, here it is 3. So what will be velocity? Velocity equal to, you will get 2 by 9 r square in bracket rho minus sigma g by eta. This is called terminal velocity of the body. This is called terminal velocity of the body. The velocity when the net force on the body becomes 0. That velocity may be 0, or that velocity is constant throughout the motion. Because if there is no net force, then the body will continue with the body will move with the constant velocity according to Newton's first law of motion. When a liquid is flowing steadily through a pipe, then according to equation of continuity, AV should be constant. Area into velocity should be constant according to equation of continuity. Why? Equation of continuity is based on law of conservation of mass. Equation of continuity is based on law of conservation of mass. Law of conservation of mass. That means mass entering should be equal to mass leaving. So we can say m1 equal to m2. Mass entering, for mass we can write volume into density. V1 rho equal to V2 rho. This should be applied for incompressible liquid. Incompressible liquid means density of the liquid will not change according to the cross section of the pipe. So equation of continuity should be applied for incompressible liquids. That only we have to study. Okay, conditions of compressible liquids are not included in our syllabus, but now need of thinking about compressible liquids. V1 rho equal to V2 rho. For volume we can write area into small displacement x at the entering A1 x1. When we are taking small displacement x1 at the time of entering to the tube, equal to rho will be cancelled, A2 x2. Small displacement when the liquid is leaving the tube, and dividing it with the time, then we will get what? A1 x1 by t is V1, x2 by t is V2. So area into velocity AV is constant. AV is constant. That means as area increases, velocity decreases. As area increases, velocity decreases. Okay. So we can say at a large area, through large area of pipes, velocity of liquid will be small, and through small hole, liquid velocity will be very large. So here you can see an example. Water falling from a tap. As the water falls down to the earth, towards the earth, speed of liquid particles increases due to gravity. If velocity should increase, then area of cross section should decrease. That is why the liquid layer, the liquid becomes thinner and thinner as it reaches towards the earth. And if the velocity becomes greater than a particular value, then the liquid falling will be irregular, or that flow is also called turbulent flow, irregular flow. Okay, the velocity below which the liquid flow is steady and after which the liquid flow is turbulent, irregular, then that velocity is called critical velocity. That velocity is called critical velocity. Bernoulli's theorem. Equation of continuity is based on law of conservation of mass, but Bernoulli's theorem is based on law of conservation of energy. According to Bernoulli's theorem, total energy of the liquid particle in steady flow, should be constant throughout the motion. So we can say PV is the pressure energy of liquid particle, pressure into volume, plus mgh, this is the potential energy of liquid particle, liquid flow, plus half mv square, this is the kinetic energy of liquid flow. This should be constant, or we can say when we are taking per unit volume, we will get P plus mass by volume is density, P plus H rho G plus half rho V square equal to constant. P plus H rho G plus half rho V square equal to constant. So we can say when the liquid is flowing through that pipe, P1 plus H1 rho G plus half rho V1 square equal to P2 plus H2 rho G plus half rho V2 square. Half rho V2 square. Okay. Then we will get the pressure difference. P1 minus P2 equal to, what will be the pressure difference? Delta P. P1 minus P2 equal to, we will get H2 minus H1 into rho G plus half rho into V2 square minus V1 square. Half rho into V2 square minus V1 square. Now, if the pipe is horizontal, here the area of cross section is A1, here the area of cross section is A2. Here liquid velocity V1, here liquid velocity V2. So, heights from the ground are same. So, we can say H1 should be equal to H2 if the pipe is horizontal pipe. Okay, H1 equal to H2, then we will get the pressure difference delta P equal to what? Half rho into V2 square minus V1 square. This is actually P1 minus P2. This is actually P1 minus P2. So from here you can see, as according to equation of continuity, A2 less than A1. A2 less than A1. If A2 is less than A1, then V2 should be greater than V1. V2 should be greater than V1. Then at which point pressure is maximum? At the starting point here P1 and here P2. Which pressure is maximum, P1 or P2? Can you say? Yes, P1 is maximum. P1 is greater than P2. P1 is greater than P2 or P2 is less than P1. How? Here we are writing P1 minus P2. P1 minus P2 equal to half rho into V2 square minus V1 square. When V2 is greater than V1, P1 should be greater than P2. Okay, to make V2 greater, A2 should be smaller. So we can say as area increases. So conclusion from the two theorems, equation of continuity and Bernoulli's theorem, we can say as area increases, velocity decreases, pressure increases. As area increases, velocity decreases, then pressure increases. And here, from here we will get a force due to change in pressure, right? Force due to change in pressure is called dynamic force. Force due to change in pressure is called dynamic force. Dynamic force F equal to pressure into, change in pressure into area. Dynamic force equal to change in pressure into area. For change in pressure we can use equation half rho into V2 square minus V1 square. So half rho A V2 square minus V1 square is the dynamic force. That force is actually used for the takeoff and for the landing of aeroplanes. Okay, dynamic force is the force due to the pressure difference due to fluid flow. That pressure difference is calculated using half rho into V2 square minus V1 square, that is P1 minus P2, and dynamic force F equal to change in pressure into area. Okay, here you can see a diagram. A pipe whose cross section is decreased at the middle B. Okay, A, B, C are the positions. Then at which position pressure is maximum and which position pressure is minimum? Can you say? We can say according to the diagram, area at A equal to area at C. Area at A equal to area at C. So we can say velocity at A equal to velocity at C. Okay, velocity at A equal to velocity at C. Area is same, velocity is same. So pressure at A equal to what? Pressure at C. Pressure at A equal to pressure at C. Now, what about A, B? Area at B is less than area at A or area at C. Both are same, right? So we can say velocity, as area decreases, velocity increases. Velocity of liquid at B is greater than velocity of liquid at A or C. So as velocity increases, pressure decreases. Pressure at B is less than pressure at A. So effectively we can say pressure at B is less than the pressures at A and C. So the liquid height due to pressure in the tubes at A and C will be larger and both will be same, and liquid level in the tube, in the small tube at B will be small because pressure at B is small. Okay, that is what discussed from the diagram. Velocity of efflux. Velocity of efflux means velocity of liquid outflow through a hole. Okay, small hole or orifice. That means area of the hole is very small. Okay, then only we can say this equation V equal to root of 2gh plus 2 into P minus P naught by rho. 2 into P minus P naught by rho, where P is the pressure inside the liquid. Okay, at the top level and inside the tank, and P0 is the atmospheric pressure. I am not going into the proof, you just by heard this equation. And now if the tank is open, then we can say atmospheric pressure is also acting at the top. P, both at the hole, at the position of hole and at the top of the tank, both are open to atmosphere. So P should be equal to P0. So this term will be 0. So then we will get velocity of efflux equal to root of 2gh. Root of 2gh, where h is, what is h here? H is depth of hole. H is depth of hole from the liquid surface, not from the lower, from the bottom. Okay, this is called Torricelli's law. This is called Torricelli's law. Here you have a question. An incompressible liquid flows through a horizontal tube as shown in the following figure. Then the velocity V of the fluid is 3 meters per second. Velocity, the liquid is entering to the tube, and then through the tube A, 1 point velocity is going out with velocity 1.5 meters per second. Then what will be the velocity of liquid flow through the tube? 1.5 A area of cross section. how to solve it. We just pause the video and try to solve. So we can say mass of liquid entering should be equal to mass of liquid leaving. Mass of liquid entering should be equal to mass of liquid leaving. So capital M, mass entering, should be equal to M1 plus M2, liquid leaving. And when we are dividing this with time, so this we can write as AV, area into velocity, okay, equal to here A1 V1 plus A2 V2. A1 V1 plus A2 V2. Initial area of cross section is A. Velocity is 3 meter per second, equal to A1 A, and the velocity is 1.5 meter per second, plus A2 is 1.5 A, and V2 we have to calculate. So A is cancelled. 3 equal to 1.5 plus 1.5 V2. 3 minus 1.5 is 1.5. 1.5 equal to 1.5 V2. So we will get V2 equal to what? 1 meter per second. V2 equal to 1 meter per second. So option C is the right answer. Surface tension. Surface tension is the property of liquid surface which behaves as a stretched elastic membrane. It is actually due to cohesive force between the molecules of liquid surface, as temperature increases, this cohesive force decreases. As temperature increases, intermolecular force decreases, so cohesive force decreases, so surface tension decreases, and the stretched elastic membrane, that behavior of liquid surface decreases. And as temperature increases to a particular value called critical temperature, surface tension becomes 0 and the liquid particle will start to become or start to convert to gas molecules. That means the point is actually boiling point. That critical temperature lies very close to the boiling point. So when we are drawing the graph of surface tension versus temperature for water, shape of the graph will be like this. Okay, this temperature is 4 degrees Celsius. This is boiling point. For this temperature we can give TC, critical temperature, the temperature at which surface tension becomes 0, and for water it is 100 degrees Celsius. And below 4 degrees Celsius, surface tension of water is not defined because water shows anomalous behavior below 4 degrees Celsius. Okay. Surface tension is defined in two methods, in two manners. First one, it is actually the force acting per unit length. The force acting per unit length on an imaginary line drawn on the liquid surface. On an imaginary line drawn on liquid surface, or it is also defined as work done to change the area of liquid surface. Work done to change the area of liquid surface. That means to bring a molecule from interior of the liquid to the surface, we have to do some work against the cohesive force. So that work done is actually stored as surface tension. Okay, S equal to work done per unit area. So unit we can give Newton per meter or Joule per meter square, both are same. Newton per meter or Joule per meter square, because Joule is actually Newton meter. So we will get Newton per meter or Joule per meter square. So to make a liquid drop, first we are discussing conditions of drop, okay, then we will go to the bubble. Okay, to make a liquid drop, we have to do a work W equal to surface tension into change in area or surface tension into 4 pi r square if r is the radius of drop, because for drop completely liquid is completely inside and outside is the air, so only one surface area is there or one free surface is there for liquid drop. Okay, and to make a, but this is the equation of making a drop, energy to make a drop, and to make a bubble, work done should be S into 2 into change in area, surface tension into twice of change in area, or we have to write S into 8 pi r square, S into 8 pi r square. Why? For bubble there are two surfaces, air inside and air outside. So two surfaces, outside air and liquid, inside air and liquid. Two free surfaces are there for bubble. So we have to use work done equal to S into 2 delta A, 2 into change in area. To change the radius of a drop, what we have to do? Equation to change radius of a drop. To change radius of drop, work done should be what? S into 4 pi into r2 square minus r1 square. S into final area minus initial area. And to change radius of bubble, work done should be S into 8 pi into final radius square minus initial radius square. So work done to make a bubble should be, or work done to increase the area of a bubble should be equal to twice the work done to make a drop, or twice the work done to increase the radius of a drop. Okay, if R2 and R1 are same. Now excess pressure due to surface tension. I am not discussing the steps derivations. Okay, just you see and you just by heard the table. Okay, for a plane surface, excess pressure should be 0. Okay, there is no excess pressure at the surface, that is why plane surface is plane, so excess pressure delta P equal to 0. And for concave meniscus and convex meniscus, excess pressure is 2s by r, excess pressure is 2s by r. And for drop excess pressure is 2s by r, and for bubble in air excess pressure is 4s by r, and for bubble in liquid excess pressure is 2s by r, because for bubble in liquid there is only one free surface, air inside the liquid, and for bubble in air there are two free surfaces. So that is why equation is 4s by r for excess pressure for bubble in air and 2s by r for excess pressure for bubble in liquid. Okay, from the table we discussed that excess pressure is inversely proportional to radius of the meniscus or radius of the bubble or drop. So we can say, as radius of the bubble or meniscus or drop increases, excess pressure decreases. Excess pressure decreases. Okay, so here you can see a diagram. Two balloons or two balls are connected. Simply if two balloons are connected, from where to where air will flow? From smaller to bigger or bigger to smaller? Can you say? Air always flows. Free flow is always from higher pressure to lower pressure. Free flow is always from higher pressure to lower pressure. So pressure is small in bigger bubble because its radius is larger, and pressure is large pressure in small balloon. So air will rush from smaller balloon to bigger balloon. Air will rush from smaller balloon to bigger balloon because air will flow from higher pressure to lower pressure. Next side heading, angle of contact. Angle of contact theta. Okay. A liquid drop is on a surface. Here we can draw two liquid drops, right? Okay. Then what is the angle of contact? Angle of contact is the angle between liquid surface and solid surface inside the liquid at the point of contact. Once more. Angle between liquid surface and the solid surface inside the liquid. Liquid surface and the solid surface, or tangent, angle between the tangents to the liquid surface and the solid surface inside the liquid. Okay, we have to draw the tangent of solid surface inside the liquid, not to outside. Okay, inside the liquid. Then that angle is angle of contact here. Okay, here also we can draw the angle of contact. Tangent of liquid surface at the point of contact and tangent of solid surface at the point of contact inside the liquid. Here this is the angle of contact. Theta is greater than 90 degree obtuse, and here theta is acute. Theta equal to 0. Theta equal to 0 degree for pure water glass pair. Pure water glass pair. Okay, and theta equal to 90 degree. Theta equal to 90 degree for pure water and silver coated pot. Silver coated vessel. Okay, and theta equal to 135 degree for mercury glass. When mercury is poured into glass vessel, theta is around 135. Correct value is 138, but for problem solving it is better to take 135 degree because 135 is 90 plus 45. Here is a note, 2 points. First point, radius of interface of two bubbles. When two bubbles come together, bubble with radius R1 and radius R2, here R1 is greater than R2. Okay, when they are combining, when they are in contact with each other, so this interface will be concave to the smaller bubble and convex to the bigger bubble. Why? For small bubble pressure is large and for bigger bubble pressure will be small. So interface will be concave to the bigger bubble and convex to the smaller bubble. That radius of interface, the radius of interface should be calculated using R1 R2 by R1 minus R2. And second point, when two bubbles combined to form a bigger bubble in vacuum under isothermal conditions, then the radius of that bigger bubble is found using the equation R equal to root of R1 square plus R2 square. Next side heading is capillarity. Capillarity. Capillarity is the change in level of liquid according to the surrounding in small holes or in small tubes, narrow tubes. Okay. And that capillarity or capillary rise is found using the equation H equal to, capillary rise is found using the equation H equal to 2S by capital R rho G or 2S cos theta by small r rho G. Capital R is the radius of meniscus radius of meniscus, and small r is the radius of the tube, and theta is the angle of contact, and s is the surface tension. This is called ascent formula. Here you can see a diagram. Concave meniscus, then capillary rise, convex meniscus, capillary fall, and plane meniscus, no capillarity. Plane meniscus, no capillarity. Okay, in concave, while the meniscus is concave, then angle of contact will be less than 90. How to draw the angle of contact? Tangent of liquid surface at the point of contact and solid surface inside the liquid, and here this is the angle of contact. And for convex meniscus, angle of contact will be greater than 90. How to draw it? Tangent of liquid surface at the point of contact and a tangent of solid surface inside the liquid. Here this is the theta greater than 90. And for plane meniscus, this is the tangent of liquid surface and tangent of solid surface inside the liquid, theta equal to 90 degree. Okay. Now this video lecture is over. Try to include all the topics, all the concepts. Okay, study material is given in the description box. Okay, next topic you are going to discuss is thermal properties of matter. Okay, so best of luck. Thank you and stay